Okay, so off we go. So here's picking up where we were last time. We're going to do another application of polar coordinate integrals. This is a really surprising application. It's really hard to see this coming. This is an extremely clever move, and I wish I'd thought of it, but I didn't. Somebody showed me this. This is a classical calculation. So the question concerns how to compute this integral. And so you might be thinking to yourself, hey, wait a minute, that's a single variable integral. Why are we worried about single variable calculus? This is a multivariable calculus class. Valid point. But bear with me. So first of all, why we care, you might recall, depending on what single variable you've had in the background, or maybe if you've had a stat class of some sort, that this is what we call the normal distribution. And it is extremely important in statistics. Not only because, we like the shape or something like that. It arises naturally, by which I mean mathematically naturally, in important, meaningful ways that we can't go off into right now. We just don't have time. But it's very mathematically natural. It's of singular importance, one way to say it. The other is it arises naturally as in physically natural, as in biologically. Heights of, corn stalks, for example. If you measure heights of corn stalks, it follows a normal distribution. So integrals, being, of course, how you compute probabilities from distributions, integrals are naturally important, and so this is a very important integral to know how to compute. And, of course, y'all will also recall we don't know how to find an antiderivative of this function without power series, which we don't want to mess with. Okay, so how do you compute this thing? And here's the clever calculation, super clever calculation, in fact. Let me see if I can get this to behave. Here we go. And let me go ahead and do this. So first thing I'm going to do is I'm going to multiply it by itself for no apparent reason. Right? But now you might object, these don't look the same, but keep in mind, x is only a dummy variable here. Right? So I could use a different dummy variable, it doesn't matter. The integral itself is the same. Okay. All right, first move. I'm going to point out that this expression right here, I don't know what the value is, but it's just a number. It doesn't depend on y. It's not a function of y, obviously, right? So being as it is just a number, I can stick it inside of the integral as numbers do. Perfectly legal. All right. Now, next, let's look at this iterated integral we've got right here. And keeping in mind that when you're looking at an iterated integral, for the purposes of the inside integral, the outside variable is a constant. We treat it as a constant because it is a constant, literally. Right? And so that means that any function of exclusively y, such as e to the minus y squared, constant for the purposes of the inside integral. And so that, whoops, I missed, that can go in here like so. Right? And so all together, now you look at what we had started with was this integral times itself, and we have now reworked that into this iterated integral, which of course is just a double integral over all of R2. If you look at those bounds, x and y range over all possible values. That means our domain is R2. And of course a little bit of algebra shows that our integrand is that right there. And so what we've done, we've turned a hard problem that we don't know how to resolve, namely, what is this integral, into seemingly an even harder problem that we also don't know how to solve. Right? And so this does not seem like we've made a lot of progress. Wonderfully, though, we're actually almost done. Here's where polar coordinates kicks in. This is why this comes up in polar coordinates. I can take this double integral, domain being all of R2, and I can just say I'm going to do that integral with a different method. I'm going to use polar coordinates. And in polar coordinates, R2 is described by these bounds. Right? Theta goes all the way around. R goes all the way out to infinity. Area, dx dy, in polar coordinates is r dr d theta. Again, perfectly legal. I haven't really done anything yet, right? But now you look at the integral, right? This integral that we're going to have to compute first. This is where we were super frustrated previously that, oh man, this e to the negative whatever square, there's no antiderivative. I don't know how to find the antiderivative. Now check it out. We have this extra factor of r, and that makes this an easy antiderivative. Just plug in u equals negative r squared. Quick little substitution, done. So it's super clever, right? This happens sometimes in math, that the best way to solve certain problems is to first turn them into harder problems. and then the point is, being a harder problem, there are different tools in our toolbox, and sometimes the harder problem is actually an easier problem in disguise. And that's what happened here. So it's a beautiful calculation. I wish I thought of it. Okay, neat little trick. So moving along, we're going to talk about cylindrical coordinates. It's a lot like polar coordinates, and likewise doing integrals in cylindrical coordinates is a lot like doing integrals in polar coordinates. We use the conversion formulas as a change of variables function. We already know the stretching factor. We computed that last time. And we know what a pullback is. And so really all we have to do is just kind of think through the rest of the details. It's going to turn out just like in polar coordinates, that instead of taking a domain and pulling it back and trying to figure out what the pullback image is, we can instead just take the slices that I would do. Here, for example, is a theta slice, right? Constant value of theta. Instead of slicing up the pullback domain, if I can just reinterpret what do these theta slices look like in the XYZ space, I can just do the calculation. I can do all the slicing in XYZ space. And this, again, is an easy problem. A theta slice, constant value of theta, in XYZ space is something like this. It's a half plane. I like to call this hinged on the z-axis, because in my mind I see kind of a sort of a door, and the hinges are on the z-axis. Okay, so half plane hinged on the z-axis. So with that understanding, and likewise, just keeping in mind that slice means constant value of the given variable, everything goes forward pretty much the same. So a couple of tips and tricks before we dive in. Again, there's some good news about your options in terms of the order for your differentials. There's really only 2 of the 6 that are worth talking about. These are those 2. You should pretty much always, let's say for the purposes of Math219, always use one or the other of these. The way you should remember what these 2 of the 6 are is that dr d theta are always together and in the usual order. And so the only thing you have to decide is if you want dz on the outside or dz on the inside. Nice, easy way to remember it. So it's just like polar, dr d theta together and in that order. And then dz, you have 2 options. So, and then again, just like with polar, even worse than with polar, there's this problem of forgetting to put the stretching factor in there. It's so common because you're going to find yourself distracted by the geometry of the slicing and the bounds. And wait a second, drawing the picture is hard and all that going on, and then you just kind of forget. Right? So the way that I advise to avoid this is always write this whole thing down all at once together. Always write down the stretching factor R as you are writing down your differentials. After all, you'll never have any need for dr d theta dz by itself without the R. It's extremely unnatural to write it down without the R. So unnatural and dangerous. So just don't do it. Okay. All right. So let's dive in. Here's our first example. We're going to look at this half ball here, described like so. Triple integral on this shape for whatever reason. how do we slice this up in cylindrical coordinates? And I'm going to do this two different ways. I'm going to do this first, dz dr d theta, and then after that I'll put the dz on the outside. We'll see how that goes down. The slicing geometry is a little bit different. But let's start with this one. Notice, as I've urged you to do, I've already put my r in there. I wrote that r down. Take my word for it, but I wrote this r down as I was writing down dz dr d theta. And I came back subsequently and thought about my bounds. Okay, so slicing. Starting with theta. Here's a theta slice. Right, half plane hinged on the z-axis. Here's how that crosses through my solid, and I get this shape right there. There's my theta slice, and now let's think about first and last. And, well, it is going to start there, where theta is 0, and then it's going to go all the way around, and it's going to end when it gets done going all the way around, right? And that would put it at 2 pi. So 0 to 2 pi in this case. Everybody happy with that? Good little sort of hack, by the way, a little memory trick, or an easy. If your solid entirely surrounds any portion of the z-axis, your theta bounds will be 0 to 2 pi. And you can see that clearly happens here. Okay, now moving along. So we're going to fix a value of theta. So we're going to leave all of our focus now on that theta slice, as we always do. Don't worry about the other theta slices. We'll get to them for other values of theta, which we've already documented we're going to do. Okay, so looking at this one slice. Next, we're going to think about R slices. What does an R slice look like? Well, an R slice is a portion of a cylinder, right? Something like that. And so, okay, an R slice here, I could imagine something kind of like that. And now you have to use your geometric imagination. What is the intersection when you take this purple R slice representing a constant value of R, and you intersect that with our existing theta slice representing a constant value of theta? How does this green sort of planar chunk, how does that intersect with this cylinder? And, well, it intersects just in this little line segment right there. Like that. So there's our R slice. Is that cool? So first and last, right? So the first R slice is here, where R is, I'm going to say, obviously 0. This first R slice, after all, being on the z-axis, R is 0. Our last slice, now you got to imagine these slices proceeding as R increases. The last slice is going to be when you're at that point right there. And so again, you got to think about, well, what do I know about this point? Now, you can play certain algebra games. You can observe that it's on the sphere. And then in addition to being on the sphere, I also see that it's in the XY plane. Thank you, picture. And you can do the corresponding algebra, and that's fine. That'll totally work. I like to make this simpler observation that the value of R at that point is actually a radius of this sphere that has radius A. And so the value of R at that point, pretty clearly just from that geometric observation, is A. Is everybody good with that? Okay, so so 0 to A. Okay, and so now, as usual, we consider an R slice of our theta slice. Looking only then at that R slice of that theta slice. Next bounds, we're going to look at Z. And, well, Z starts at that point, which is in the XY plane. Thank you, picture. Pretty clearly Z equals 0 at that point, so that's a freebie. The not quite a freebie is if I'm looking for the upper bound for z, that's going to come from this point. And again, here I really have to think about the picture. What I can see from the picture about that point is that it's on this surface. It's on this sphere that has that equation. Now, don't forget the critical last part of the bound finding process, and that is to recognize that what I need this point for, what I need this equation for, this is really easy to lose track of, but don't forget, I'm solving for a z bound. So within this equation, I need to solve for z, and now that's not that bad of algebra here, but very importantly, we're solving for z, and that is why that is our z bound right there. Everybody all right? Okay, and we win. Okay, now we're going to do it again. This time we're going to do it with the slicing in the other of our two option orders. Let's see here. I could do it about like, there we go. So this time with dz on the outside instead of on the inside. So now different geometry because we're doing the slicing in a different order, and z slices look different from theta slices. So the geometry is going to be different. The mechanism, right, sort of the pattern, it's exactly the same. So starting with, what do z slices look like? Constant value of z, right? I appeal to your geometric intuition. A z slice of this ball. Whoops, I kind of missed the thing there. Okay, anyway, a z slice of our ball is a disk, like so. And again, first and last, I think it's an easy pitch that the first slice is down here, where pretty clearly z is 0. Last slice is up here at the North Pole, as it were. That's at the top, which again, that being a radius, means z is the radius, namely a. So there's our z bounds. Is everybody all right? Alrighty, now we fix a value of z. We consider now only this z slice. Moving on to the next variable. The next variable is theta. Well, pretty easy pitch, I think. Theta goes all the way around. Is that cool? Is everybody happy with theta goes all the way around there? So 0 to 2 pi. And then lastly, now I have to look at a theta slice of my z slice. And okay, all right, now let's think it through. The z slice is this disk. A theta slice of the z slice represents, looking just in one theta direction. In other words, looking, inside of that disk, I want to take the intersection with a angled theta plane like that, and that intersection is going to give me just a little line segment like so. And so again, thinking about r, now our inside variable, r starts at that point where r is pretty clearly 0, right? And r is going to end at this point. And okay, it's easy to lose track of what you're doing here. Wait a minute, what is that point? Picture tells me it's on my sphere again. So I'm again going to look at this same equation, exact same equation. But again, easy to lose track of what you're doing, but don't forget, we are trying to solve this time for r. R is now our inside variable. So I'm going to solve for r, not z, in this equation. And solving for r, I get that, and that's my inside r bound. Everybody okay? Yeah?
If I feel more comfortable doing it in theta slices, like always, would that be dangerous? Like
Dangerous.
What situation would you want to do each one?
Right, great question. So remember, when we're looking at our slicing options, whatever variable you put on the inside, you're going to have to solve for that as a function of whatever's further to the outside. right? And so sometimes it'll be the case that z will be naturally, conveniently understood as a function of r and theta, right? But sometimes it's really the other way around. Sometimes r might much more naturally be thought of as a function of z. That could totally, depending on the shape of what you're looking at. And if that happens, then you need r on the inside. Yeah, so I understand the temptation to pick a favorite and just kind of stick with that, but you're going to get in trouble. Yeah, there are going to be questions where you'll be out of luck and just can't get that anymore. Okay, great question. Okay, let's see here if I can get this to cooperate. Come on, here we go. Okay, spherical coordinates. A lot of the same ideas. The conversion formulas are a change of variables function. We've computed the stretching factor. We know how pullbacks work. But instead of pulling back and then slicing up the pullback, we could just see what do the slices look like in XYZ space. So really all we need to think through is, for example, if I look in the theta direction, if I look at a constant value of theta, what does that look like? And well, we already know that one. That's what a theta slice looks like, right? And now we just have to think through the others. What does a constant value of phi look like? I've got to think geometrically here, but phi, keep in mind, represents angle off of the z-axis. So constant value of phi would actually give you a cone, I argue. And that's a little creepy, right? That's geometrically unappetizing, I think. But that's what it is. This is what a phi slice looks like. And then likewise, what does it look like if you take a fixed and constant value of rho? Well, a constant value of rho is going to be a sphere. And that's an even weirder looking slice. Right? Hard to imagine a knife that would make a cut that's that shape. Okay. All right, so that's the bad news. Here's the good news. Actually, there's a couple of bits of good news. One is, of your 6 options, there's really only one order that you need to worry about. And I've done, in my physics days way back when, bazillions of spherical coordinate integrals. It turns out that spherical coordinate integrals are crazy useful in physics, right? And having done a million of these, I've never needed to do them in any order other than this, right? So I suggest that you don't even think about your other 5 options. You should always, certainly in this course anyway, do your slicing in that order. So you don't have to think through all the different combinations. And here's the better news. If you do your slicing in this order, the ugly geometry that we just saw it resolves itself pretty nicely. So for example, here is a theta slice. Right? Now let's think about what does it look like if I take a phi slice of my theta slice. How does this cone intersect with that plane? Well, line. Straight line. Not that bad. Right? No big. And then how does, what happens as I look at successively larger values of rho, successively bigger spheres, emanating out of the origin? You might say, well, no problem. That just represents, along that slice of the slice, it just represents going outward in the rho direction. So not that big of a deal, not that bad for a slicing process. A bunch of other stuff, highly expected, super easy to forget your stretching factor. So hedge against forgetting by always writing these down all together. Right? You're going to have this temptation to say, yeah, I'll worry about the integrand later. All the stuff inside the integral, well, that's a later problem. I want to write down my differentials so that I can think about my bounds and get lost in the geometry, and then you're going to forget. good odds anyway, you're going to forget that stretching factor. So write it all down all at once. Again, this one thing by itself is worth significant points just by itself, right? So don't leave those points on the table. Just go ahead and grab them. Always write this down all as one thing. And again, by the way, this is natural mathematically because this by itself is not a thing. You will never need to write down just d rho d phi d theta. If you're using spherical coordinates to compute an x, y, z integral, you always need the rho squared sine phi. So write it down together. Otherwise, if nothing else, you're writing down unnatural stuff. So urge that you please always do that. Okay. All right. So let's see a slicing process. Okay, here's our domain. We've got this ball of radius A centered at a point A on the z-axis, like so. Right, there's our solid. Let's think about theta slices of our solid. So a theta slice looks like this. All right, thus giving us this kind of a cross section, this kind of a slice, you might say. And now, question: for what values of theta as I go around do I get a slice? And well, of course, all the way around. Again, easy to see geometrically. After all, this solid entirely surrounds part of the z-axis, so theta is going to go all the way around. Thus. Everybody happy? Okay. All right. Okay, now, little math hack. You don't have to do this. I find this helpful. Everybody's different, whatever, suit yourself. But I find it helpful to take this picture of my theta slice and the resulting piece of the domain and to redraw it. Oh, if this will behave. Here we go. To redraw that looking straight on at it. Right? So what's awkward about the top picture is that I'm looking sort of askance at it, right? I mean, this plane is kind of facing off that way, and I'm looking at it at some sort of a weird angle, and some unnatural stuff happens. For example, in space, I know that that is a right angle. It doesn't look like a right angle on the page, though. That's confusing, right? That can lead you to get some wrong answers. Now, it can make sense out of it as long as you remember and as long as you're thinking geometrically and thinking three-dimensionally. Yeah, it's fine. But I do think it's easier to look at it in a way where what are right angles will always look like right angles. I just think that's easier. So this is what I do. You don't have to do it. Okay, so looking at our theta slice, again, our theta slice being this. Let's think about what phi slices look like, and phi slices come out of the origin like that, as we previously discussed. Keep in mind, phi is represented by an angle like that. That's what phi is. All right, and so with that in mind, there is my first phi slice, and my phi values, as I slice more and more, as I move along, right? What a messy thing that is. But as I proceed along, you can see these phi slices are getting shorter and shorter. The closer you get to horizontal, the shorter these phi slices are getting, and they disappear finally at phi equals pi over 2. Is that cool? Everybody happy? Yeah. Mm-hmm.
Why is it ZR in the...
Oh, yeah. Yeah, so that's a kind of a visual aid. I'm calling this the R-axis. It isn't really... There isn't really an axis there, but that's the direction in which R is increasing. So, I mean, it's a little sloppy, but conjures an image. So, yeah, I was just pointing out that when you're looking straight at it, is what that is right there. Yeah. Okay. Okay, so so 0 to pi over 2. And now, fixing our attention on a phi slice of our theta slice. So now just looking at that, let's think about what rho does. Rho starts at this point, which of course is that point, which, by the way, don't lose sight of the fact that that's that point. Right? So it's really the origin. In my little sort of convenient sort of redraw, this is the origin, where, of course, rho is 0. Yeah. And then, okay, let's see, we're going to end at that point, and that point's on that curve, which, okay, now wait a minute, but don't forget, that curve, right, is actually this curve on our original picture. In other words, our point is on a curve that's actually part of the sphere. Right? And so if I want to understand what I can say about rho on that point, I need to understand the spherical equation for this sphere. And this is a chapter 1 problem. You've got to take this information right here. Right? You can write down the rectangular equation for our sphere, given that you know where the center is, and you know where the radius is, and rectangular coordinates are easy for writing that down. And once you have the rectangular equation, you can use chapter 1 methods to turn that into the spherical equation for that sphere. Now, I just swept a bunch of details under the rug, right? Make sure you can do this. Make sure you can write down the original rectangular equation, you can convert to spherical coordinates, chapter 1 methods, and then you'll get this as your result. Again, since I'm looking for a value of rho, we solve for rho, and there's your upper rho bound. Everybody good? Okay. Cool. So let me try to make a sales pitch here. I think the picture is really important, right? I hope these examples that I've done here are persuasive, and you can see how much we really need to rely on the picture. These pictures that I've drawn are plenty good enough for our purposes. They're not beautiful, right? They don't look as good as if a computer had done it, right? But as far as getting work done, they're plenty good enough. And being able to draw a reasonably good picture is just unavoidably helpful. It's in multiple ways. It's not just that you will be able to visualize the problem better if you have a good picture. That's certainly true, right? But also keep in mind, you have to be able to communicate your thought process, right? And so, for example, if I had just written this down, that alone, where's the thought process? Whoa, what did I just do? Where is the thought process that led to this if I just write that down by itself? It could be totally right, but there's no thought process. There's no justification. There's no reasoning of any description. Right? So you got to give me something. And in cases like this, I think the picture is actually pretty much the point. So notice in the work that I've done here, actually, let me zoom out where we can see all this on, well, come on. Here we go. Notice in the work that I've done for this question, very little text. I didn't explain in paragraphs, right? But you can see what my slices look like. If I draw this and then claim that theta goes from 0 to 2, I think this communicates a lot of ideas. I think it's pretty clear. This is the thinking that justifies that result. Right? So don't think of drawing the figure as something that you do to help yourself, while it is, of course. Think of it also as something you do that is required in the question to communicate your reasoning. So drawing a good picture, again, very, very important. Don't try to get away with a teeny tiny little picture. A lot of students will give me pictures that are like, okay, well, let's see, here's my axes, and there's my sphere, and there's a slice And then here's a slice of my slice. And then now I see the page, and there's the picture that I'm supposed to interpret from. Right? Come on, that doesn't communicate much. Too small. Hilariously too small. Right? So make your pictures comfortably large. No little teeny tiny postage stamps, please. And then, try to do a decent job with it. So try to make it as clear as you can. Also, don't expect that you can do it all at once. Right? When I make figures, and anyone who's ever come to my office hours and asked me to draw the figure for whatever, you've probably seen I go through stages. Right? I take a hack at it based on what I'm seeing in the given statement of the question, and then I realize what's gone wrong with my diagram, but I've learned something from it. And then based on what I've learned from my bad first attempt, I make a second figure that's better, incorporating what I've inferred from the first one. And then that helps me learn even more about what the picture looks like, and then my third one might be the one I actually go with. As recently as a couple of days ago, I went through 6 iterations before I finally got a decent, acceptable picture. Right? So you should be doing something, you should be expecting anyway that you'll have to do something along those lines. So don't forget, on the exams, the backs of the pages are yours to answer questions with. And don't forget as well, you have scratch pages. Right? And if you want to, practice, do your sketch drafts on the scratch pages first, so you can kind of see try to understand the shape, and then draw your final figure, in the space provided for the question. That'd be a perfectly reasonable way to go. Okay. Lastly, a lot of people mistakenly think that being able to draw mathematically is some sort of inborn talent. I do not believe that. It certainly isn't for me. But I picked up techniques from various different places, right, over the years. And so you're probably going to need to do this too, right? You'll probably need to learn the techniques. Now, I don't claim to know everything about drawing these kinds of figures, but I think I know a lot. I think I've collected a lot of good knowledge, and I've put everything that I know in those recordings in the miscellaneous topics playlist on my YouTube channel. So I encourage you to watch those recordings and notice the very valuable insights and tricks for how to make a good drawing that I discussed there. Also, this is not something that you can just kind of watch someone else do and then just be good at it, right? Think of it as kind of like a sport in a way, and you have to practice, right? It's one thing to watch someone do a cool dribble move in basketball, and it's yet a very different thing to be able to do it yourself. So give yourself the time. The homework exercises, of course, will force you to take a certain amount of practice. I would encourage you to do your own additional practice if you think it's necessary. Okay. All right. Moving along. Let's see here. Okay. So, next solid. Another ball, radius A, different center. This time then the ball is like that. The slicing of this is going to be totally different. That's how it turns out. Notice for one thing that this entire ball, the whole thing, is to the right of the XZ plane. Right? In fact, you might say that this ball kind of, it just barely touches the XZ plane exactly at the origin. Right? So when you start thinking about the theta slices here, the theta slices that will generically look kind of like this, for theta slices like so, those are really only going to go from the 0 angle to the pi angle. So theta is just going to go from 0 to pi. Now, that's a highly geometric appeal, right? I'm not algebraically demonstrating that. And I'm not going to say it can't be demonstrated algebraically, but I am going to say it would be an awful lot of trouble to make an actually persuasive algebraic argument that theta goes from 0 to pi without the picture. I think that would be extremely difficult. So, again, I mean, if you're going to write down something like this claim here that I'm making, that theta goes from 0 to pi, like so, you got to give me some sort of a justification, and a decent figure along these lines, I think makes a great case for it. And so being able to draw a figure like this, it's unavoidably critical. It's just critical. So make sure to build yourself up drawing-wise to the point where you can actually do something kind of like this. Okay. All right. Okay, now we're going to look at a theta slice. And again, I'm going to redraw because it's confusing to try to think about angles when I'm looking at it at this distorted sort of side view. So I'm going to redraw that theta slice over here, and here's my cross section, my theta slice. And now let's start thinking about phi slices. Generically, phi slices look about like that. And again, you can look at the picture and think about first and last. I think the pretty clear first value of phi is going to be there where phi equals 0. All right, and then my last phi is going to be, well, I mean, you think about how these slices proceed as you move along. And I think the last one's going to be straight down where phi is pi. Again, that's just a geometric appeal. Thank God we have a picture that we can make the appeal based on. Right? And 0 to pi. How are we doing? Does everybody see how the picture makes that case? Okay. All right. Then, as usual, we look at a phi slice of our theta slice. We think about first and last. Obviously, rho is going to start at that point. Don't forget that's actually that point, which of course is the origin, which has rho, therefore, starting at 0. Our last point is going to be there, which is on that curve, which is actually that curve, meaning that the point we're looking at there is actually on the sphere. And again, you have to, there's a bunch of work that I didn't put on the page here, but you're going to have to take this sphere, described by this information, write down the rectangular equation, go through all that chapter 1 conversion, convert to spherical coordinates, and I claim that the resulting equation of that sphere is there. And again, make sure you can do that. It's really not obvious. And you just got to go through the algebraic process. So, and again, solving for rho gives me my upper bound for rho, like so. Does everybody buy it? Okay, super quick last observation on this example. Notice, and I didn't say this as I was doing it, but I assert that when I wrote this example down, this was the very first thing that I wrote down. Stretching factor included. Get that on the page first. Don't take any chance that you're just going to leave those points unclaimed. Okay. All right. This last spherical example is really just a kind of a geometry thing. I'm not going to go through all the details on this. There is some spherical trig algebra kind of stuff that you got to work out. I don't want to spend time on that. We've already done enough of that. But there is an artistic trick here. And what our solid looks like is this thing right here. It's the part of one ball that's outside of another ball. And that's a weird thing to draw. This is actually a poor picture. If you think about, if you had a scoop of ice cream, right? And if you were then to take a spherical ice cream scoop and scoop a hole down out from underneath, right? There would be kind of a edge, kind of a lip down at the bottom, and so there's really kind of solid all the way down around here as well. But how do I draw that without making it look like it's filled in solid? It's tricky artistically, right? So tough draw, and then further tough to imagine. Something that's hard to draw. How do I imagine what the cross sections look like if I can't even draw it? Right? So I think that's tricky. So here's the big idea. When you are looking at what I'm going to loosely call an intersection, right, and you want to take the cross sections of that, like so, as we need to do, the really clever point is to realize that you don't have to actually think about your actual solid and then slice it up. You can slice up the original components. That'll be easier. And then just look at how they intersect. So specifically, if I ask, forget about the actual green solid. What is the cross section of that sphere? Oh, that's easy. That's a half a disk. What is the cross section of that sphere? Another half a disk. Right? So what I'm really looking at here is how that intersects that. Right? I'm going to look at the intersection of the cross sections instead of trying to deal with the hard to deal with cross section of the original intersection. So it's just it's a nice little bit of geometry, and so I just wanted to point out that this really helps with the art. Note how obvious it becomes that what I actually need is this, and furthermore, I can see what the edges of this thing look like, because I can see that it comes right off of these circles, which come right off of the original spheres, and the geometry becomes much more palatable. Okay, think about the rest of these details. This is a nice exercise. I'll point out very quickly that we got lucky again. There's another equilateral triangle to take advantage of. Always be on the lookout for that sort of good fortune. And we're going to move on now. Well, no. Let's see, how much time do we actually have here? I've got 3 minutes. Okay. As behind as we are, we need this. Let me just remind you all of the theorem you already know. By the way, before I get into that, this is still section 5.5. There's a really powerful computational technique that I want to spend some time talking about because it's really important. Because I used it a bazillion times in a physics major, and a lot of y'all are engineers, and you're going to be doing a lot of morally equivalent integrals, and this is a super important trick to be aware of. The book, I think, undersells this point. In fact, I think most multivariable calculus books underemphasize the value of what I'm about to show you. So this is all my thing, but I think you're going to appreciate it in the long run. Here's the theorem. The theorem says that if you have an integrand that is odd, reminder, this is what odd means. Flashback to single variable calculus. Right? And if you have a domain that is symmetric, and symmetric, you can think of that in different ways. The way this tends to show up in practice in single variable calculus is that it's an integral from negative a to a, or negative c to c, or something like that. The lower bound is the negative of the upper bound, or the way I would prefer to think about it, when you reflect over the origin, it doesn't change. It is its own reflection over the origin. Okay. So when that happens, if you have an integral on a symmetric domain with an odd integrand, your integral is 0. Right? Done. No anti-differentiation necessary. No integration by parts, no substitutions. Just 0, walk away. So this is a really powerful theorem. Now, how much does this get used in a Calc 1 class or a Calc 2 class? Yeah, not that much. I agree with that, right? But in a multivariable calculus context, and this is just sort of a justification of the single variable, in a multivariable calculus context, there is an analogous theorem right here. Analogous theorem that if you have a function, an integrand, that is odd, and we're going to have to make sense out of what odd means, and we'll do that after spring break. And if your domain is symmetric, and we're going to have to make sense out of what symmetric means, again, we'll do that after spring break. Then again, we get this very powerful conclusion, and that is that our integral is 0. And drop the pen and walk away. And this has saved us a tremendous amount of effort, and this theorem really does come up a lot. Like in practice, in the real world, in the the countless integrals that I did as a physics major way back when, I'm going to say I think a conservative estimate, 20% of the integrals that I had to write down, I could argue, oh, that's 0 by symmetry. 20% of the integrals. That's a lot of integrals. So very, very valuable. We'll talk more about this next time. Y'all have a great spring break. See you in 10 days. Have a good one.